the finite intersection property, which is abbreviated as FIP. Definition: a family, say F of some subsets of a set capital X, is said to have the finite intersection property if for any n element of set of natural numbers and F1, F2, etc. Fn element of family F, the intersection Fi over I varying from 1 to n is non-empty. So from this definition itself, we can observe that every member of a family having FIP is non-empty, since every member can be regarded as a finite intersection of that member with itself, and hence that intersection should be non-empty, which will imply that that member is non-empty. So we can conclude that every member of any family having FIP is non-empty. Examples: if space X is a topological space, and if we represent by Nx the collection of all neighborhoods at a point small x, then Nx will have FIP, since any finite intersection of members of Nx will definitely contain the point small x, and hence the finite intersection will be non-empty. So Nx has FIP. Now if we consider the family of all closed disks in the plane which contain the origin, will have FIP, since any finite intersection of members of this family will contain origin. Proposition: if a family F of subsets of a set X is closed under finite intersections, then the family F has FIP if and only if phi does not belong to the family F. For the proof, let us assume that F is a family of subsets of X which is closed under finite intersections. First, assume that the family F has FIP. If phi were a member of the family F, then any finite intersection of members of the family F, which includes the particular member phi, will be empty, a contradiction to our assumption that the family has FIP. Therefore, phi cannot be a member of the family F. Conversely, assume that phi does not belong to the given family F. Now, to prove that the family F has FIP, consider an arbitrary element n from the set of positive integers and choose n elements, say f1, f2, etc. fn from the family in random, and consider the intersection of these members. Since this family is closed under finite intersections, this finite intersection will belong to the family F itself. But we know that phi does not belong to the family F. Therefore, this intersection over I varying from 1 to n f phi cannot be equal to phi. That is, this finite intersection is non-empty. And hence we can conclude that this family F has FIP. This completes the proof of our proposition. Next is a characterization of compactness in terms of families having FIP. Proposition: a topological space is compact if and only if every family of closed subsets of it, which has the finite intersection property, has a non-empty intersection. Thus we can see that this proposition is a characterization of compact spaces. For the proof, let us assume that X is a topological space. Suppose first that the space X is compact. then we will need to show that every family of closed subsets having FIP will have a non-empty intersection. For this, let us consider a family, say C, of closed subsets of the space X and assume that this family has FIP. We have to show that this family has a non-empty intersection. That is, we will need to show that intersection C over all C element of this family is non-empty. If possible, assume that this intersection, that is intersection C over all C element of family C, is equal to phi. We know that by De Morgan's law, the complement of this intersection, which will be equal to union over all C element of family C, X minus C, and that will be equal to complement of this set, that is complement of phi, which is equal to X itself. That is, we have obtained that the union of sets of the form X minus C, where C element of family C is equal to X. Or we can say that the collection X minus C, where C element of family C covers the space X. Since family C is a family of closed subsets of the space X, we can observe that these sets X minus C are all open subsets of X. So this collection of all sets of the form X minus C, where C element of family C is in fact an open cover of the space X. But we know that the space X is compact. So every open cover will have a finite subcover. Hence this open cover also will have a finite subcover. Say X minus C1, X minus C2, etc. X minus Cn, where C1, C2, etc. Cn are all members of family C. Since this collection is a finite subcover of the space X, the union of these sets will be equal to space X. That is, we can write union of sets of the form X minus Ci, where I varies from 1 to n, will be equal to X. Taking complement on both sides and applying De Morgan's law, we can see that LHS will be equal to intersection over I varying from 1 to n, complement of X minus Ci, that is Ci itself, and that will be equal to X complement, which is equal to phi. This means that a finite intersection of members of family C is in fact empty. This contradicts the fact that C has FIP. Therefore, our assumption that intersection C over all C element of family C equal to phi must be wrong. That is, intersection over all C element of family C must be non-empty. This proves the direct implication. Conversely, assume the given condition. That is, we assume that every family of closed subsets of the space X which has the FIP has a non-empty intersection. We will need to show that space X is compact. So, we will have to show that every open cover of X will have a finite subcover. Let U be any open cover of the space X. Now consider a new family, say C, which is defined as the complement of U, that is X minus U, for every U element of family U. Then C is a family of closed subsets of X. If possible, assume that this family has FIP. Then by our assumption, since this family C is a family of closed subsets of X having FIP, this family C has a non-empty intersection. That is, intersection C over all C element of family C is non-empty. But we know that every member of family C is of the form x minus u, where u element of the cover u. So this intersection is non-empty. If we take complement on both sides, we will get intersection over u element of family u, x minus u whole complement is not equal to phi complement, which is equal to x. And by De Morgan's law, this complement of intersection will be equal to union of complements. Complement of x minus u is u itself, and that is not equal to x, which means that the union of all members of the family u is not equal to x. This is a contradiction since u is a cover of x by our assumption. This contradiction shows that our assumption that C has FIP must be wrong. So we can conclude that the family C does not have FIP, which implies that there exist finitely many elements of C, say x minus u1, x minus u2, etc., x minus un, such that their intersection I varying from 1 to n x minus ui is equal to phi. But we know that intersection over I varying from 1 to n x minus ui, that is intersection of complements of sets of the form ui, is equal to union over I varying from 1 to n ui whole complement, or we can express it as x minus union over I varying from 1 to n ui, and this is equal to phi. That is, we have obtained that the complement of this set is equal to phi, and this should imply that the set union I varying from 1 to n ui is equal to x. That is, we have obtained that the collection u1, u2, etc. un is a cover of the space X, and we can see that this is in fact a subfamily of the open cover U, and hence we can see that this is in fact a finite subcover of the cover U, and thus we have proved that every open cover will have a finite subcover, and hence we can conclude that the space is compact. This completes our proof. The previous proposition gives us all the machinery we need to prove the characterization of compact spaces. This characterization theorem states that the following statements are equivalent. First one says that X is compact. The second statement is every net in space X has a cluster point in space X. And the third property is that every net in X has a convergent subnet in the space X. This theorem claims that these three statements are equivalent. We are going to prove that 1 implies 2 and 2 implies 1 first. The equivalence of these two statements, that is statement 2 and 3, follows from a previous theorem in which we had proved that a point, say small x, is a cluster point of a net if and only if their x is a subnet which converges to the same point. From that theorem, the equivalence of these two statements, statement 2 and statement 3, are obvious. So, it remains to show the equivalence of the statements 1 and 2. We know that X is a cluster point of S if and only if there exists a subnet of S which converges to X. Therefore, statement 2 is possible if and only if every net, say S, in the space X has a cluster point, say small x, and that is possible if and only if there exists a subnet of S which converges to the same point X. That is possible if and only if every net S has a convergent subnet. Since we had chosen this S as an arbitrary net in the space X. That is, we have proved that 2 is possible if and only if 3 is satisfied. Now, to prove the equivalence of 1 and 2, let us first prove that 1 implies 2. Here we assume that space X is compact. We need to show that every net has a cluster point. So let us consider a net, say S from D to X. We need to show that S has a cluster point. We know that if X is a cluster point of the net S, then for any neighborhood U of X and for any n element of D, there will exist some member, say M element of D, such that M follows N and S of M element of U. Now here, in order to show that S has a cluster point in X, we assume that this particular net S does not have any cluster point. That is, we assume that X is not a cluster point of the net S for every X element of the space. Then the negation of this condition will hold. The negation of this condition will be obtained by replacing this for all by their X's, and we will be able to say that there will exist some neighborhood of the point small x and some element of the directed set such that for any member of the directed set which follows that particular element, corresponding member S of M, corresponding element of the net, will not be a member of that neighborhood. That is, we can say that for any X element of capital X, since that point X will not be a cluster point of our net, there will exist a neighborhood, say Nx. For convenience, we assume that the neighborhood is labeled as Nx of the point X and an element, say Mx with the subscript X, element of D, such that for all n element of D, n follows Mx implies that S of n does not belong to the neighborhood Nx, or S of n belongs to its complement x minus nx. Using this argument, for every x element of the space X, we have obtained a neighborhood Nx of X. So we will be able to cover the space X using these sets Nx. That is, we can observe that this collection of all such sets Nx will be a cover of space X. We know that the space X is compact. So this cover, which consists of neighborhoods, will also have a finite subcover. So there will exist some finitely many elements, say x1, x2, etc., xk from the space X, such that nx1, nx2, etc., nxk forms a finite subcover, and this will imply that their union nxi, where I varies from 1 to n, will be equal to space X. By our assumption, we know that for any x element of X, there exists a neighborhood nx of x and an element mx of D such that for every n element of D n follows mx implies that S of n belongs to x minus nx. So this statement will be satisfied for the points x1, x2, etc., xk also. That is, for I varying from 1 to k, that is for the points x1, x2, etc., xk, nxi's are neighborhoods of the point xi's, and there will exist mxi from D such that for every n element of D, n follows mxi will imply that S of n element of x minus nxi. So corresponding to x1 there is an element mx1 from D. Similarly corresponding to x2 there will be mx2 from D and so on. Let the corresponding elements in D mx1, mx2 etc. mxk. Because D is a directed set, there will exist some n naught element of D such that n naught follows mx1, n naught follows mx2 and so on, n naught follows mxk. Or we can write n naught follows mxi where I varies from 1 to k. But we also know that whenever n follows mxi, corresponding element S of n will be a member of x minus nxi. Here our element n naught satisfies this condition. N naught is an element which follows mxi. So from the previous observation we can write S of n naught will be a member of x minus nxi, and this is true for every I which varies from 1 to k. Or we can write S of n naught is a member of intersection over I varying from 1 to k x minus nxi. And we know that by De Morgan's law this is equal to complement of the union over I varying from 1 to n nxi. And since the collection nxi forms a finite subcover of our space, their union nxi will be equal to x itself. So this is in fact x minus x itself, and that is equal to phi. This implies that S of n naught belongs to the empty set, which is a contradiction. We have arrived at this contradiction because of our wrong assumption. We had earlier assumed that x is not a cluster point of S for any x element of our space. That is, we had assumed that the net S does not have any cluster point. This assumption must be wrong. Hence, we can conclude that the net S has a cluster point. Thus, 2 holds. This completes the proof that 1 implies 2. Now it remains to show that 2 implies 1. Conversely, assume that statement 2 holds. That is, we assume that every net in the space X has a cluster point in the space. We need to show that the space X is compact. By a previous proposition, to show that a space is compact, it is enough to show that every family of closed subsets of it which has FIP has a non-empty intersection. To prove this condition, let us consider C a family of closed subsets of space X having FIP. Let us construct a new family, say D, which is the family of all finite intersections of members of C. Since C has FIP, phi will not be a member of D. Also, the intersection of any two members of this family D will again be a finite intersection of members of family C. Therefore, D will be closed under finite intersections. Also, we can observe that every member of family C will belong to family D. Hence, C is a subfamily of D. Now, for D and E, element of family D, let us define a new relation. D follows E to mean that D is contained in E. Since follows here represents the inclusion relation, it is obvious that this relation is both reflexive and transitive. Also, we can observe that whenever D and E are members of family D, D intersection E is again a finite intersection of members of family C, and hence it will belong to family D, and D intersection E will follow both D and E, since follows relation is in fact the inclusion relation itself. So, corresponding to any two members of family D, there exists a third element from the same family D, such that the third element follows the first two elements. That is the axiom 3 of directed sets. Thus, the relation, follows relation which we have defined, makes our family D a directed set. Now, let us define S from family D to X by S of capital D equal to any point in the set D. This function is well defined since capital D will be non-empty for every D element of family D, as we had observed earlier. Thus, S is a net in the space X. By our assumption, statement 2, we know that this net S will have a cluster point, say small x, in the space X. We claim that this cluster point X will belong to intersection of all members of family C. To prove this claim, we assume that X is not a member of this intersection. Then it implies that there exists some C0 element of family C such that X does not belong to C0. Therefore, X belongs to X minus C0. But we know that C0 is a member of family C, and hence C0 is closed in the space X. Therefore, X minus C0, its complement, is an open set in the space X. Hence, we can say that X minus C0 is a neighborhood of the point X. Also, we can see that since C0 belongs to family C, and since family C is a subfamily of family D, C0 will belong to family D also. Thus, we have a neighborhood X minus C0 of the point small x, and we have a particular member of our directed set, namely C0. Then, by the definition of cluster point, since X is a cluster point of the net S corresponding to this neighborhood X minus C0 and corresponding to this particular element C0 of the directed set, there will exist some D element of family D, our directed set, such that D follows C naught and S of D element of this neighborhood X minus C naught. But we know that D follows C naught implies that D is a subset of C naught, and S of D element of X minus C naught, where X minus C naught is contained in X minus D from the inclusion D subset of C naught. That is, we have proved that S of D belongs to X minus D. Or we can see that S of D belongs to the complement of D. So S of D does not belong to D. A contradiction. Since we have defined S as S of U is equal to a point in U. So S of D should have been a member of D. Thus we have arrived at a contradiction. Therefore, our assumption that X is not a member of the intersection of all members of family C. This assumption must be wrong. So our claim must be true. That is, X must be a member of the intersection of all members of family C. And this implies that the intersection of all members of family C must be non-empty. Thus, we have proved that every family of closed subsets of X having FIP has non-empty intersection. Thus, the space X will be compact, and hence we can conclude that 1 holds whenever 2 is satisfied. This completes the proof of 2 implies 1, and this completes the proof of our theorem.